No es del aire.
¿Ah?
No, pero es del aire. Este no está poniendo más.
All right.
Sí.
Good. Any announcement? Anything? Any? No. Good.
Remancho, any announcement today?
Announcements?
Anuncios, algo que quieras que se necesite por acá.
No, me llegué temprano ya. Sí, lo que
If you want.
muchachos, recuerden que la idea es que después de la última sesión, todos, la gran mayoría que creo que todos ya están en el grupo, vayamos al sitio con el profesor Mati a parchar y ya. Ya. ¿Preguntas? Bueno, la idea es que lo que tú tomes lo pagas. Y ya. Sí, ya también. ¿Ya? ¿Una otra cosa? ¿No? Sí.
Okay, we are live.
Are we doing some sort of group picture or something like that?
In the afternoon.
In the afternoon? Okay, good. We'll do this in the afternoon. All right, then good morning, everyone. Friday morning, still some people around. I think some of you also have exams now, so busy day. Today will be probably a bit less busy. I'll be covering a few topics that I find interesting, or things that people in my group, that's kind of things we are working on now. So we'll be talking about the rest of the week with more general things. Now a bit more recent research, and then we'll see where we go and some tutorials to do as before. So that's what we are.
Sorry, just a little. Just a few. Yes, maybe this will better.
Okay, thank you.
But that needs some more effective solution.
Yeah, we can also leave the door open if it helps.
Yeah, maybe.
Okay, so as I said, today just a few general things on more modern topics in modeling and a bit of future things that especially, I can't cover everything, but more like things that I'm interested in, things we do in my research group. This afternoon we're gonna just continue with sort of kind of things we were doing yesterday, with sci-fi issues, a few other things we can look at with the simulations. Okay, before we start, just check. questions or anything from yesterday or any other day? Anything else you would like to know about? No? Good. You changed that?
Yes.
Okay, just as a motivation to get us started, and also because you guys made some simulation images and movies yesterday looking at the different components, so I did dig out another simulation. So it's a sort of similar simulation, but showing a different way of looking at the results. So what we have here is again largely structure, but what I've done is been just changing, showing you on the one side. Right, there's a diagonal in the middle. It's the same simulation, just continues, but on the one side I'm showing the dark matter, and in the top right I'm showing the gas. Right. So some of you have made images like that yesterday already. They were probably on different panels, or some of you looked at the dark matter and the stars. Okay, so one is just inspiration for what we can make. But I think the other interesting thing you can see from this already from just the still image here before I play it is the way that everything is distributed, right? So you can see that the dark matter forms much smaller structures as well. So you have all of these filaments. You can see that this big filament here is seen both, but on this side you have all of these tiny structures with all kinds of small halos, but they're not really seen on the other side. And the reason is that not all of this, so the dark matter only follows gravity, right? So it will collapse and form structures on all scales. There'll be very, very small halos everywhere. But some of these halos are too small to contain any gas. The gas is too hot in the intergalactic medium to just follow gravity. So gravity is not strong enough to make this gas collapse into these halos. And so the background here in the gas region looks a lot more smooth. Right? To give you an idea, so this is dark matter. It's just people like to show it in purple for reasons. And then on the gas here, you can think of here I've used 3 different colors for 3 different temperature ranges. So blue is about 10 to the 4. Green is going to be like 10 to the 5, 10 to the 6 Kelvin. So this is where a lot of the cooling can happen. And then red is even hotter gas, like very something that you will probably see if you had an X-ray telescope, for instance. Okay? So you can see that mostly a lot of cold everywhere. In the filaments, the gas, what we would call something like water, 10 to the 5, and then close to the halos, where there are these bubbles created by these galaxy formation activities, we reach much higher temperatures. So now so just to give you the context, this is so not doing a rotation or something, it's just a time evolution. So you have time since the Big Bang here, and if you prefer redshift, it's also given down there. So you can see even I stop here, it's redshift 5.6, which is 1 year after the Big Bang. Already there is a lot of structure in the dark matter, but really not much yet has happened in the gas. So the dark matter, because it only has gravity, will collapse first, and then once the potential becomes large enough, the gas will go to fall into these potentials, cool down, and start forming galaxies. Now, and then we should start seeing some larger bubbles of red and hot gas happening because of aging activity, like we discussed yesterday. Okay, so really, the important here is the contrast between all of the structures that are in the dark matter and all the stuff in the gas. So, for instance, if you are now making an experiment, and you want to learn something about dark matter, say you have a different theory of what dark matter is, you make it warm, for instance. What does warm dark matter do? Warm dark matter removes a lot of the small halos because it has velocity, so the particles themselves velocity, so the warm dark matter will cancel a lot of the small halos. But that's going to be very difficult to observe because in the gas and in the stars, we don't see them anyway. And so if you wanted to observe all of these tiny blobs, because your theory of dark matter says they don't exist, or there are more of them, or they are a different shape, or whatever. That's what you can hope to see on the top right. The bottom left, you will have to somehow infer it in some way. It's going to be a lot more difficult. Shall I do this again? Or
Yes.
Yeah. So very rapid collapse of the dark matter stars, forming these filaments and structure is growing, and then as the potentials get large enough, you can start forming halos which are dense enough to cool down from galaxies and then expel some matter by our particles. Any questions? Anything that we hear is weird, strange, interesting?
Listen, sorry, when you say about those little purple dots in the dark matter density, if I don't know, if I'm super powerful and I just throw in those spots gas, they have to be but the gas will be in that, well, you know, like battery in that spot because of the
So if you take one of these,
potential of the gravity of that point.
right? So if I take these blobs, say this tiny blob here, and so I go in there, somehow have all magic powers, and I put some gas in there, why would it not stay in there? So you're right that fundamentally, so there is gravity, so it should stay there. But why isn't that working here? Any suggestion?
Maybe gas is still too hot
Correct.
to just be attracted to.
Correct. So this is exactly what is happening. So even though the gas is labeled as cold, cold is still 10,000 Kelvin, right? And where do we get that temperature from? We discussed the other day that there is this constant flux of photons, both on the CME, but also for just all of the other galaxies in the universe everywhere. And so that's enough energy, enough photons to keep the gas, especially because of a lot of UV photons. So we call this the UV background. So if you go in a completely empty region of the universe, you start measuring how much light there is, there's always enough light in the UV range to sort of keep the gas to about 10,000 Kelvin. Okay, so it's not going to cool down. And so if your halo, what you can do a calculation, and you can ask, okay, see, here's a halo of a given mass, so it will have a given potential. Well, you can ask how much pressure or temperature will be able to resist that gravity. And that will essentially give you a threshold between the halos that are completely dark, that we never see, and the ones that will have just a couple of stars, and then of course the much bigger ones. And that in principle is only set by understanding atomic physics, right? If you understand the light and then the way that the atoms can transition between levels, that will tell you what can cool, what can not cool, and different temperatures. So this is actually something that has very little to do with cosmology. We understand these processes extremely well. What is the halo that can form a star? But since you asked, I have another question then. Can we observe these in some way?
The purple spots?
Yeah, the smaller ones, right? So these, I said we cannot see them in the gas. They also don't have any stars, right? Since they don't have any gas, they never cooled down to form a single star. So but my theory says there should be all of these blobs everywhere, right? There should be millions of them everywhere I look. That sounds like something I would like to test. Because otherwise maybe you have a different theory of dark matter, where they don't exist, but I couldn't tell the difference. So that doesn't sound very satisfactory, right? So can you think of a way, or is there a way we can test some of this?
Maybe, I don't know, a little interaction between, I don't know, this is the spot.
Yeah.
I have gas here or anything I can see.
Yeah.
And the other way, maybe a small interaction in the edges. I don't know, is the.
Yes, good idea. Anyone else? So first of all, it's very, very hard, but there are two ways people are trying to do this. One, are you familiar with gravitational lensing? So if you have a very heavy object, say a big galaxy, light that is coming from something behind will travel around it, right? The light will travel around it, okay? So that we see. We see all of gravitational lenses, that's very well understood. Now imagine that you have a big galaxy here, the light is going to go around it, but here on the path, there's one of these tiny blobs. So instead of just making a perfect distorted image, there will be a small disruption in in the image which is already disturbed. Okay, so the idea that if you understand well enough all of that physics, you should be able to measure what is the mass of that small blob that is on the way. That is an extremely difficult measurement, so far it hasn't been done. But you could imagine that if you have a theory of dark matter where there are no small halos, then all of the images in lensing will be very, very nice, because there will be nothing to disturb them. So just measuring the level of disruption is one way of doing it. The other way, I think, is closer to what you had in mind. But that you can only do, for instance, inside our own Milky Way. So with the Milky Way halo, of course, the Milky Way has the galaxy disk, and that's the most of the stars. But there are also stars that happen to be just randomly in the halo. And some of them form strings, especially if you have a globular cluster that came in, so a group of 10,000 stars or something, it is going around the Milky Way very far away from this, to just insert an orbiting potential. As it goes through a potential, we lose stars, and we form very long lines of stars that follow the orbit. Think of a bit like the ring of Saturn, right? So if you put it something and you start disrupting it, it will create a long ring of stars along the orbit of that globular cluster. Okay, these are called stellar streams, and then you can do the experiment you have in mind. If there is one of these tiny blobs passing by one of these streams, which we will see a gap in that line of stars. Because something that you don't see, right? If you see something, of course you know, okay, there was a black hole or a big blob of star, but maybe there's something you don't see that made a hole in that stream of stars. And then you can say, here there's a gap, and if that must mean, or that could mean that some dark matter halo has passed by, so I can try to measure the mass. Some people are interested in these gaps, and some people that think it's impossible, they call this the gapology, like the study of the gaps, and they're making fun of them. So who knows whether it will work? It's like the word Big Bang, right? The word Big Bang is because someone who didn't like the theory at all, so it was fun to call it Big Bang, because it's going to be a bad theory. So all the theory is completely wrong, it's the Big Bang. So maybe gapology is going to be the right thing, that is the way that, the word is going to stay, and it's going to be correct, because it works. Okay, let's just play this. Yeah. Good. So maybe some inspiration for this afternoon. If you want to make your own images of simulation, you can use different color maps to show different things. It's quite interesting if you want to highlight. Right, the goal is, because in simulation you have all of the information you want, people can choose color scheme to show exactly what they want, and that's very useful to get some good information. It highlights the information you want. Okay, now I want to go to the next one. Okay, so today, selection of modern topics, as I said. So let me start with just a few things that are things that we work on in my group. Can maybe switch on the light here? Thanks. So this is more on the, so in my group we both do a bit of running simulation and do a bit of cosmology, but also we think a lot about developing codes, like the one you guys have been using this week. The software we developed a bit, so we're always thinking about what is the next piece of physics that we should be adding in our simulation to get things more precise. And so on Tuesday we talked about how we can simulate gravity. On Wednesday we talked about dynamics. And there are two other things that for sure people say are important, and I agree that we really need to go to the next generation of simulations. One is magnetic fields, and the other one is radiative transfer. So I'll describe just quickly what these are. I guess magnetic fields you already know, but out of interest. Why do we care? So here's a very cool map. I like it very much, it's very beautiful. So this is from the Planck collaboration. So the Planck satellite is often known because it measures the cosmic magnetic background very precisely, and we got very precise information about the best fitting cosmological lambda-CDA model and all kinds of other things. But the other thing the satellite did is it measured polarization, which is just the twisting of the light on the way, which is due to magnetic fields. And most of that twisting on the way actually comes from our own Milky Way. And so they've been able to make a map of the Milky Way and of the magnetic fields. So what you see here is, so we are the Milky Way, but we are not in the center. So if you look, it's again this question of what is this map? This is sort of the whole sky, but if you peel an orange or a fruit and you just open it up, you get a map like this. And so that's the galactic disk. The center of the Milky Way is here. We are looking at the disk from the side because we are almost on the side of the disk, right? So this is out of the disk, down the disk. And what you see here in the color is the intensity of the magnetic field that they measure. But you also have all of these lines showing you where the magnetic field lines are. Okay? And so that's very interesting because we can look at this and we can ask something like our models, can we understand where this magnetic field come from? What is the physics behind that generated these? And also just an observation, for many of these things, there's some sort of a pollution because they're distorting the light on the way. So if you really want to make precise measurements, we may have to remove the effect of the magnetic field, so we need to understand the magnetic fields in the first place to do this. Again, also if you think about charged particles, so they are also, for instance, like black holes or other high energy events emit very high energy particles like protons or electrons that are high velocity. And because they are charged, they will follow the magnetic field lines. So they will travel along the field. So if you want to also understand where these particles come from, what they're due to, and so on, we need to understand what are the routes, what is the path they can follow. So understanding this is quite interesting, and it's quite important if you want to make some progress. What I like about this image is that, because I'm in the Netherlands, it looks like a lot like a painting of Van Gogh, this sort of painting style of lines. And the other thing I like about this famous Starry Night, but if you remember on Wednesday, we ran a simulation that was also doing sort of the Kelvin Helmholtz instability. So I don't know what he was seeing that night, whether he saw a cloud at that same thing, or I don't know, maybe he was drinking something pretty good, but or he was doing simulations, I don't know. But somehow it's also in the painting, so we should be simulating these things. Okay, here's another example. This is not from another galaxy. I think this is M51, where the same thing has been done. So this is this is just observed light. And the right here, it's a bit difficult to see, but you have all of the contours showing you the intensity of the magnetic fields, and you also have tiny arrows that show you the direction of the magnetic field. And so what is quite nice with this one is, for the Milky Way, we see it from the side. This one we see it from face-on, so we get a different idea of how the magnetic fields are oriented in this galaxy. And if you look closer, you can see that there are, of course, the magnetic fields seem to be turning around with the galaxy disk, and there are also different levels between whether you're inside a spiral arm or outside of a spiral arm. Okay. So there's something we'd like to understand there as well. Okay, so magnetohydrodynamics, I like this from this KCD. So magnetohydrodynamics is combining the equation of magnetic fields with hydrodynamics. And I quite agree with what they say here. So they say, well, the sun's atmosphere, the superhot plasma governed by hydrodynamic forces. And the comment says, whenever I hear the word magnetohydrodynamic, my brain just says magic. And that's sort of true because the equations are very non-intuitive, right? I think we all, as some humans, have an intuition for how fluids work. But as soon as you think about magnetic fields, how all kinds of weird effects happen, you're like, I don't understand. I don't have a good mental picture of why some of these things work and some of these effects. So sometimes some of these things you see in simulations or in real experiments, they really look like magic, but actually they are understandable. Okay, so let's dive a bit into this magic. What is it that you want to do? What that we want to do? It's this. Okay, so the other day we looked at the earlier equation for just a simple gas. Now it's the same thing. It's actually, this is even a simplified version because here it's a version without any of the viscosity in the fluid. And it's also with some approximation for the magnetic fields. So now we have 1, 2, 3, 4 main equations that tell us how things evolve. So we have something that tells us how the density evolves, how the velocity evolves, how the energy evolves. We have 3 like that already for the earlier equation. We have an additional one telling us how the magnetic field evolves. The magnetic fields enter these equations here as well. And then just some relations that tell us that the total energy also contains magnetic fields and gets complicated. Now, if I do this, that's what we had on Wednesday, when we look at the fluid equation. So if I just say B equals 0, this whole thing reduces to what we know from the earlier Boltzmann equation for fluid, right? So that at least is a happier land, something we understand a bit more. but also it shows you that there are B coupled everywhere through, and especially there are all kinds of crazy things, like there's a nabla cross B cross B, right? This kind of complicated high order derivative and operations that you have to take on this. So it can get quite messy quite quickly. And also B is a vector, so you have to be very careful. What do we do with this? Any hope? Any suggestion of what we could do with such a mess? Actually, we know the solution. Well, we don't know the solution to the equation, but we know a way forward. So on Tuesday we discussed that every time I see, if we remain on the side of doing our simulation in hydrodynamics by a particle of an SPH, we discussed that every time we see some operator, whether it's acting on a number or on a vector or something, we know how to translate that into an SPH operation. And so that any of these grad or a div or something can be replaced by some function of the kernel double. So what I can do here is just blindly apply the rules. Just say, I trust that the rules I derived are fine, and just walk through and get a set of equations that will work. Okay. And that's what you can do, and it actually works. It works out to be correct. The other thing you can do is, we also talked on Tuesday. Remember, at the start of the derivation, we say, let's write a Lagrangian for a system that was kinetic energy minus the thermal energy of the system. What I can do here is that I can also add this B dot B over 2. This is the magnetic energy of my system, or for these particles. So I can extend my Lagrangian and have an extra term that is just B dot B over 2. And then I go again through the whole machinery of using Lagrange theorem and so on, and I will derive a set of SPH equations that have the correct shape, and that also ensures conservation of energy and all of these things. So that part is actually not too bad. It just looks scary with a lot of terms, a lot of combination of quantities, but that is doable. Okay? And also just easy to test, because if you for instance, setting B to 0, you should recover the normal setup and so on. So it's well understood. What is more complex and what comes next? The problem is with Maxwell's equation. Oh, that shouldn't be shown here. Okay, so let me stand here so you don't see this bit. So the Maxwell equations, you already know everything. I'm sure you know. I think some of you have made from dynamics exams today or something, so this is a good summary. So, is there anything problematic that you can think of that can happen with the Maxwell equations? Shouldn't wear a white t-shirt, that doesn't hide anything. Anything that is weird or unusual? It's a subtle question.
It's more on the notation, right? That E, what that H means.
Yeah, so well, it depends on it's sort of this, yeah, the different, this is, think of this as being B, this is E, no, this is B and this is E. This, yeah, it just depends where I did my copy pasting from. So the problem is not with the notation. Okay, the main issue, the main complexity of this, right, is this part. Div B equals 0. So if you look at all of the equations we have looked at before, they're always telling us, if we put the previous slide, all of these equations are some evolution term. So E, how is E going to change? How is V going to change? How is rho going to change? Equals something. Right? I can always move all of this on the other side, and that tells me how a single quantity will change in time. Okay? So that tells me how I should change V, B, E, and rho. Okay? That one doesn't have any time derivative. This is just saying us, at every point in space, everywhere, I must have divergence of the B field equals 0. Okay, so it's not like telling me how to change B. It's telling me, if you change B, you have to make sure that this is true. Otherwise, you're not solving the Maxwell equations correctly. So it's sort of constraints on how you change things. So it's not a dynamic equation. It has to be true all the time and everywhere. Okay, so now, why is that a problem? The problem is that if I take the other equations, right, all of these derivations in numerical equations, they're always approximations. So we're making an approximation to the correct truth of how rho changes, or v changes, and how b changes. So if I have now a situation where this is true everywhere, but I try to evolve my field to the next step using this equation, right? I have an equation telling me how the vector b is changing with time, but this is not going to be infinitely precise. There'll be some approximation because I used particles or because I used degree or something. As a consequence, that will not necessarily be true, and actually in practice will almost never be true, because you're always making small mistakes, so you'll always generate something where diff of b is not going to be 0 on the right-hand side. Now, why is that a problem at all? So, well, it's a problem fundamentally because we would like to solve the Maxwell equation and not something else. Right? And then typically that would be saying there are monopoles in our universe, so they are like something some people would like, but usually we don't want to do this. Saying, right, the reason this equation says there is 0 on here, it means that there are no particles, just positive magnetic field, just negative magnetic field. You always have a dipole, you always have a magnet, like a bar, like a magnet, have a plus side and a minus side. You cannot have just a plus. And so by simulating and making mistake in the approximation, we are generating region of space where there's more plus than minus, or more minus than plus, right? We're doing something in balance, and that is meaning where our evolution is going to be completed. Okay, so that is the main difficulty to simulate magnetic field. Irrespective of what technique you use, this is the main problem people fight against all the time, trying to find a way to make sure this equation is true everywhere all the time. Yes?
That again.
Which part?
Why is different?
Why it's difficult? Okay. So I'm trying to, let's imagine I know B everywhere, right? And I'm going to use this equation to tell me what is B at the next step. Now this, so it would mean dB by dt is equal to nabla cross B cross B. Let's say I'm not, my approximation in the calculation is not very precise because I'm not using enough particles, or I'm not using a good enough grade, or I'm using dt which is too large. Then the B I get at the next step is not going to be infinitely precise. And so it's not guaranteed at all by just evolving this equation that if I now go into my next step and calculate diff B everywhere, that's going to be 0. Because we made an approximation somewhere. And so then maybe this, and that will create problems down the line, because then I end up solving something different than what I wanted in the first place. Okay, so there are two solutions to this, and a lot of debate in the literature about what is best to do. One is called cleaning, is to say, whenever we find a region of space where diff B is not 0, I'm going to add some equations in my code to kill off the diff B. And so typically what people do is they add an extra field that sort of works as detection, and then they will transfer, they will convert that diff B into some sort of wave equation and sort of dissipate. It looks very much like if you throw a stone in a river, you see ripples, so you get this diff B that it was a spike somewhere, and it just evaporates slowly over the whole space. So you are doing some mistake because this is obviously not true in the Maxwell equations. There is no such thing in a Maxwell equation. But the cost is to say this is better than letting diff B being non-zero for a long time. Okay? So it works well, but it means we're not actually solving exact MHD equation. We are adding an extra field to solve our problem in the first place. Okay? So then it's usual. It's sort of, we discussed the other day what we do for viscosity, that we want to only apply it at the right place. So there's a lot of discussion about where we add these things and what are the consequences. The other solution, I think, is more beautiful, but it's much more complex. Sorry, here's an example of what I was saying. So if I start a field where there is some divergence of B, then it will keep evolving. But what I can do, I can add this term and I can make it disappear, sort of a sound wave, and sort of dissipate my mistake. slowly over time. The other solution is considering the vector potential. So I don't know if you have seen something like that in your electrodynamics classes. Yes, okay. So instead of solving the equation for B, I can solve the equation for A, right? And then we say that B is curl of A, so nabla cross A. Right? And that is good because div of curl of A is always, well, div of curl of anything is always 0. So div of curl of A is going to be 0. So by construction, we get this. The problem is that the equations for A are a lot more complicated than the equation for B. So maybe yes.
Are you calculating those operations even for a person?
Yes,
So
always.
it's still to have something.
Correct.
Zero.
Correct. So there are two things indeed. So we are solving the equation for A, which are more complex. And then if I do calculate div of curl of A, it's not going to be 0. But because we are solving the equation for A, not for B, it doesn't matter that we make a mistake because it has no dynamical impact. The div B does not enter the evolution of A, if you want. So it's okay, but it's a lot more complex. And also you have a question, you have to do a gauge choice, right? Because when you define A, it's defined up to a change of gauge. So which one do you pick? Gives you different answers, possibly, and you have to be careful whether it creates a lot kind of problem. So what we are doing in our code is that we are trying to do both. We have two versions of the MHD equations so that we can compare. We can run twice the same simulation and we can see if they give us the same answer, then we can say, okay, it's probably okay. And as soon as they give us a different answer, we can say, well, we have to be careful because we don't know which one of those two approaches is introducing possibly a mistake, maybe both. But something is going a bit strange, so we should maybe stop looking and or try to understand what kind of effects are happening. So here's an example from one of the things we do. So here's a galaxy. I showed you before the M51 galaxy from like a face-on. Same thing here. So it's a simulated galaxy. You have the spiral arms, and then we put in magnetic fields, so we can do these kind of things. But I think you guys more. We can look at the large scale structure for later. It's more interesting. And so here's more philosophical question, maybe, or early universe question, or something. Where do these magnetic fields be? Where do the magnetic fields come from? What is the origin? So the ionized gas definitely carries the magnetic field, but if you look at the equation, what the equations do, the Maxwell equations, they twist the field, they amplify the field, but there's nothing that creates a field from there. I can change the shape of the vectors, I can do all kinds of things, but I'm not like suddenly creating a field out of nowhere. So the field had to be already there before we have Asma?
I'm thinking about a concentration goal for electromagnetic field.
Yeah.
Something like that, maybe an explosion. Something was verified. It's some kind of social, I don't know. The energy is changed and something to the magnetic field.
Any other ideas? So the main answer here is that we don't know. Okay? We don't know where. So what you suggest is possible. There are also models where we say there are fields coming out of very early on, coming out of inflation just after the Big Bang. Somehow some process created this. Some people will say when the universe is at about, I forgot what the temperature is, when we create the first in leptogenesis, when we start creating particles, if you actually do the calculation in detail, which is apparently very difficult, you can create some field at that point. I don't know more about that. This is like quantum field theory calculations that I don't understand. Some people say maybe it's unrelated to this, maybe it happens later on, maybe when stars start being born, some other effects can create magnetic fields. Some say it's due to black holes. So the answer is we don't know. We know we observe some magnetic fields. One thing we can think about is that, for instance, if the magnetic fields are created in the process, like you mentioned, due to stars, for instance, then probably there should be only magnetic fields inside galaxies and not really in empty regions. Whereas if it started from the early universe, there should be magnetic fields everywhere. So maybe we can start distinguishing these scenarios if we have very detailed measurements of things. And of course, we also need the theory, the simulation model, and everything to be able to make predictions that we can compare. Okay? But that's a big question. We don't know. It's a big open question in cosmology things. Anyway, here's a movie. This is just showing you. So we have seen some of these before, like large-scale structure, filaments, and everything. But now, instead of coloring by density of the gas, this is showing you the magnetic field strengths. So they made a choice. They decided magnetic fields existed since the Big Bang, and they made them evolve via some sort of similar equations that we looked at. And then they can give us some prediction for where they think the magnetic fields are. So in that kind of models, it's mostly aligned with the filaments, but of course it gets much more intense as well inside the galaxies. The main thing that makes magnetic fields grow is just because by collapsing and making the gas more and more dense, it will also carry the field with it. So the first order, if there's dense gas, there'll be a lot of field, but it might be also other effects.
Where I can see the magnetic field that's
The intensity of the color is the B field. It's like the norm of the vector.
okay.
They're not showing us the vector, just telling us what is the sum, the intensity of the B field. Okay? So, I mean, from this kind of model, you can say, well, it looks like the normal density field or like the temperature, which is what is one of the results, is to say, if you keep things simple enough, then the magnetic fields will be at the same place as the hot gas and the dense gas. So that's a nice prediction you can make, and then people can go and test that and see whether this is exactly how things behave.
So basically, the gas is like a complete.
So the gas is a hot plasma, right? So the most of the magnetic field is going to be carried mostly by the electron in the magnetic field. So if I compactify my gas, right? If I make it more dense by the same process we discussed yesterday, then I will also just carry my magnetic field. But then can be additional effects that are only related to B field that make it more. So we call this a dynamo effect, where you start not just coloring with density, but just the B field itself can be enhanced. Yes?
This model considers the radiation into changes in magnetic.
No. No, this is too big. Not yet. Okay, and then maybe just a few words on the other topic. So radiative transfer. That is the fancy word for saying light propagation. And so far we just assumed that, well, we haven't assumed, just completely ignore the fact that light travels, there are photons and things that can happen. And so here the goal is to add on these models the effect of light propagation, the emission, scattering, and absorption. And so why do we care? We could say, well, light just goes yes.
Just a question to the question that I just made.
Yeah.
This means that the solutions that you gave us, the simulations, may be wrong in the sense that maybe the norm of the vectors of the magnetic field aren't too high into this radiation that just reduce the energy of the magnetic field.
Yes, so I don't know what the magnitude of that effect is. So you would have to actually combine sort of light propagation solution with magnetic field, and then you can couple the effects. Try to remove some energy from the B field and put it into the photons. I don't think anyone has ever tried to do this. But that's how you would observe it, right? For instance, we observe the magnetic fields via the polarization of light, or via something like a Zeeman effect. And all of these, you probably, if you were to have an ultimate simulation with everything, you would probably need to include that also as part of the equation, because we are indeed removing some energy from it. Okay, so what the idea here is that we talked about yesterday that one of the key processes is cooling to govern galactic formation, or when cooling or heating. So we have the gas, and it absorbs photons or emits photons, and it will change its temperature, which will have all kinds of consequences. And so, in most of the models, what we assume is that the light is the same everywhere through the whole universe, because that's easier and we don't have to do any calculation, but that's clearly wrong. If you're inside a galaxy, you get more light from stars around you than if you're in the middle of an empty region. Same if you're next to a black hole that's emitting a lot of X-ray, that should affect the gas more than completely other random region of the universe. So you probably have to take this into account if you want to go into more details. And so you want to be absorbing some of the light. Right? So the stars emit some photons, they get absorbed on the way, which means they will heat or cool down the gas on the way. And after that, the photons, once they're fully absorbed, you should stop. You should stop cooling or heating the gas beyond that. But also, when we now heat up the gas via some line emission, this is also going to radiate away in a different wavelength because now the gas is hot. So it's a very complicated process that combines all kinds of atomic physics again, but also propagate. So there are all kinds of channels that need to be taken into account. Okay. So one of the main challenges, first problem, the speed of light is very fast. So we talked yesterday or Wednesday about the fact that if you have a grid, you don't want to miss information. You need to take a time step in the simulation is small enough that nothing really travels between the cells too fast, between time steps. Okay? But the speed of light is really, really fast. So if I want to enforce that condition, I need to take very, very small time step to make my photons not miss any patches of gas in the way. Sorry? The simulation never ends. So there are very, very few simulations that go all the way down to the present day. Many simulations stop at version 10 or something. Because then they have exhausted all of their computing time. It's a very expensive simulation to do because of exactly that condition. Okay, the other thing is that we just don't want just photon. Photon information is useful, but what we want is to know whether the photon is emitted is in X-ray photon, or the UV photon, or it's the Lyman alpha line, right? So you need to be tracking all of the different frequencies. So now that means that you need a lot of information on each particle for each of the frequency to know how many photons in each particle have X-ray frequency, UV frequency, radio frequency, whatever. So that's a lot of data. So then you have to add it. Your simulation becomes very, very expensive in memory because you want to track all of this information. And then on top of that, you think of, because we're doing cosmology, and the universe grows, we also have to redshift the photons, so they will change bands. You have to add a lot of processes to get them correct. And then, because the main goal of doing the photon transfer is to calculate the cooling, and now that we have the photons, we can do it correctly. That leads to a lot of actually extra math operation. We have to do a lot of computing to make use of all of this extra information. Because instead of now having just a patch of gas and say, okay, this is the average density, we know how it cool by using some tables. Yesterday afternoon, when you run the simulation, you have to download one of these tables. The cooling table that says if the gas has this density at this temperature, it should cool down at this speed. That is a good approximation, but on top, it's better if you know that if it has this radiation coming from Lyman alpha and this amount from Lyman beta and this amount of radiation from X-ray. Instead of using a table, we can actually do the calculation from atomic physics to tell us exactly what is the cooling rate. But that's a lot more. We know exactly what these equations are. It's not difficult, but it's a lot of math. So it's a lot of operations that the computer has to do on top of what we are doing in a normal case. So that makes it very expensive because we have a lot of time steps, a lot of data, and a lot of math operations to do. So as you said, no simulation ever finishes in this case. So it's a very difficult problem. So you have to find all kinds of approximation. One of the classic approximations everybody uses is so-called reduced speed of light. So we're not going to simulate everything with speed of light to be c, but we're going to take 1% of the speed of light, or 10% of the speed. And for some cases, it's okay, depending on what science case you want to do. Right? For instance, you can think of if you are within a galaxy and there are stars everywhere, the fact that you get the light from this star or from this star, which is closer, doesn't matter because there's an average pass of photon everywhere. It doesn't really matter because the speed of light was not quite correct. But if you're trying to say how far do the photons go outside of the galaxy, there is no other star, then you have a problem. So yeah, depending on the science case, here you can say I'm only going to track one band, one photon energy, because maybe I only care about line alpha, or one specific line of my cooling. Then you could say I'm going to track one number. But what is the main science goal? One of the main science goals of this, especially related to cosmology, is to look at realization. Are you familiar with realization? Yes, no? Okay, so.
It's the thing that happened the universe was black.
Correct, so that's between redshift 10 and redshift 7. We don't, the exact redshift is still to be worked out. This is where the first star, some of the stars have already been born and are starting to emit enough ionizing photons to change to react to ionize all of the gas around it. Right? So what you have at this point, you already have small halos, small galaxies everywhere, and they are starting to emit photons that are going to change the ionization of all of the gas around it. So what is going to happen is that you have the galaxies and you have bubbles of photons escaping the galaxies and changing the ionization state of the gas around it. So that's something we'd like to understand. So that's what this simulation is showing. So the time evolution is very short, it's not a very long time, but what you have is that this is a very big region of space. And what you see is that growing bubbles of gas that is changing from being atomic to being ionized. So you want to simulate exactly this, because what people do then, so for instance, one question here is that at a given point in time, what is the fraction of space which is ionized? It's a fraction of space which is blue versus dark. So then if I go and do observations and I find maybe 20% is, I can go and test whether my models are correct. Okay, I can try to assess at what time the whole universe becomes ionized. So the good thing is, because this happens at relatively high redshift, we don't have to run the simulation all the way down to redshift 0, so it saves your makes your point, but these are still very expensive. Okay, so very important for realization, early galaxies and also dispersed galaxies that are affected by the same processes, and also the gas within this I mentioned before. If your blob of gas in the galaxy is close to the center, for instance, it will receive a lot of X-ray photons from the black hole, or if it's close to a star, it will behave differently. So you can't just model the entirety of the gas as just one single, as only one single source of light. We have to, in principle, take into account where that gas is with respect to the stars. Any questions on that part? No? I forgot what I had next. Okay. Couple of words on that, and then we'll take a coffee break. So, I think that is quite fun. So, one of you made the point, I think on Monday, that what are the patches of the CMB that we simulate? How do we know it's our universe? Something like that, right? So, what we have done, and you've done this on Tuesday, we generated random Gaussian fields to make initial conditions. And every time you press the button, you get a different Gaussian field, and all of them are valid realization of the universe. They all have the correct power spectrum. They all have the correct information, but they are different realizations. One of them will generate maybe a big halo, some of them will create a lot of small halos, right? They are just random We haven't put any constraints. So one question you could ask is there a way to not make a random universe, like all of the movies I've showed you so far? Can we make our universe? And by our universe, I mean a universe where we have, there'll be a halo, which is the Milky Way, and a halo, which is the Andromeda Galaxy, and a halo, which is the hypercluster at the right distance, and a coma cluster at the right distance in this direction, and the Perseus cluster over there at the right distance, and so on. So instead of drawing random numbers entirely at the start of my initial conditions, I want to be drawing cleverly selected random numbers, such that when I evolve the simulation forward, I get our universe. And it can also be an interesting question. You can also say, right? Some people are thinking about this and saying, maybe it's impossible, and then we test our model, right? If I cannot find a way of generating the correct random numbers to get our universe, maybe the theory is wrong. We're not there, but that could be an interesting question. Or we can also ask, what is the likelihood? If you think completely in Bayesian way, you can say, what is the likelihood of observing our universe given a lambda CDM field? Okay, so as I just said, we looked at random simulation. In a tutorial, we generated Gaussian random field and used them to make a starting point of the simulation. Yes?
I have an idea, maybe it's more important, but how about, I didn't download the first lecture. Someone asked, how about to see the past of our universe
Yes.
and have those data
Yeah.
past?
That would be one way of doing it. It doesn't work well, and I'm going to come to why in a second. And so, as opposed to random simulation, we call constrained simulation a run or a simulation where we choose the phases of the random field in a clever way to look like something we want. Okay? So the difference between a random or anomalous and a constrained simulation. So how does it work? So power spectrum is given by lambda CDM model, so that we know how to calculate. We did this. We didn't do it ourselves, but we know how to do this. We know the initial power spectrum. We generate random numbers for the phases. Then we evolve by a simulation, like we have done on Monday or Tuesday afternoon. Okay. Then we can look at it and say, okay, now I see a filament. Here I see a halo. Here I see this. Does it look like my universe? Does it look like the Perseus cluster, the coma cluster, the Broad cluster? Unless you were unbelievably lucky, it will not. So what you do is that you say, okay, you can try to summarize this into some sort of statistical statement, but that's just a more formal mathematical way. But you can say, okay, that doesn't look like my universe. What section of my initial conditions do I need to change to make it look more what I want? And so then you go here and say, okay, if I want more mass here, because I would want a cluster in this region, then probably I need to put a bigger CMB fluctuation at that point. Here, if I want a big void here, I need to make it less dense at the start, and so on. Then you run again, maybe it looks a bit better, and you keep going until either you run out of research time, or you get bored or something, and you can get a lot of time. It's very, very complicated. Right? So we have done one, I'll show you some images in a second, where we made initial conditions where we had 256 density points on each side, so that's 16 million free parameters. So we have to choose what is the CMB looking like patch on 16 million different points. So you have 16 million numbers. So when you feed a function, when you feed a line, you have two numbers to figure out. Here we have to figure out what 16 million numbers are to give our own universe. It's a very, very big fitting problem. So now, why can't we go backwards? And you could say, okay, let's take the final correct universe, simulate gravity backwards to see what it looks like. So there are two. The main issue with that is that the data is not good enough for this. And what we mean by not good enough? We know where the galaxies are, but we don't know their velocities. Or we can only get only part of the velocity. We only get the velocity maybe along one of the axes and not along the other two. Right? Because measuring, nothing moves on the sky, so we only have the redshift direction, the rate of direction, not the other two directions. So we don't have enough information to say this has to move, because we don't know, we're missing 2 out of 3 components of the vectors. That is not enough information to start and then just run backwards. Doesn't work. If we could measure the other velocities, it would probably work well. You can do some simple things. It's not precise enough compared to just random guessing and trying. So there is an example from the Hestia collaboration where they do only a small region. So what they're interested in is simulation of the Milky Way, M31, which is the Andromeda Galaxy, and M33. Oh, that picture is terrible. I'm sorry. But essentially, they essentially construct a region of space which looks like the distribution of galaxies around us, because they're interested in the detail of what's going on here. And you can say, well, okay, the galaxy is here, but M31 is not very, very far, so maybe there is some influence. Maybe it's not, when we want to do something specific about the Milky Way, I should not just take any random halo. Oh, here's another question for you. What is the mass of the Milky Way? Do we remember now? 10 to the power 12, right? So a lot of people, when they want to simulate the Milky Way, they take a random 10 to the 12 halo out of a big simulation, and they simulate that with a lot of details. But these guys say, well, maybe that's a bit dangerous because this is not very far, or not far enough that it may have some influence. Maybe we should be careful and not just select any random 10 to the 12 solar mass halo, but just one that has this environment. And they constrain the simulation to look like that. Here's one that we did from the Sidalis project. And this is now showing, this is a much larger region of space. So this is real data. Every blue point is a galaxy. And so we are observing here, we're observing in this region of sky, is the region of sky the telescope can see, so it has this strange wedge shape like. And this is our simulation from the same region. It's not perfect. There's still work to do. But the idea would be that this wall here is here as well. This sort of stickman figure is here as well. And so this is sort of this where we are in this field of trying to make bits of universe that look like what we want. Convinced? Good enough? I don't think it's good enough. But it's not good enough yet, but it's getting there. Right? There's just the same thing, but now as seen from the Milky Way, same simulation. And again, we are sitting at the Milky Way looking at the whole sky. The color in the background is dark and white, as we have seen before, it's just a dark matter. So now white is very dense, you can see you can see many halos around here. And then on top of that, what we have done is that red dots are real galaxies. Okay? So if we say galaxies have to live in the bigger halos, then we can see that in our simulation, we got the halos at the right place where there are big galaxies. So we did a relatively good job at simulating a universe that is our universe and not just a random universe. So you can find a Perseus cluster here, Fornax, Virgo, whatever cluster you like to look at. So which is also interesting because some of these clusters are very nearby, so there's a lot of data. So we know a lot of things about the Perseus cluster in observation. So if people want to compare simulation to observation, it's better if you have a Perseus cluster instead of a random cluster because it has the same history, it has the same shape and everything. It can be quite useful. Questions on this part? No? Then let's grab a coffee.
So you're right. Sí, calma. No, es muy clarito. Sí, sí, sí.
¿Sí o no? No, no. Sí, no, no sé, no. No, sí, claro, claro.
discriminación en ¿sabes? Yo para la ley de
Lo ganan, ¿sabes? Lo ganan. Ahí.
Los profesores son condescendientes. El profesor ya está calificando, está hablando.
No a calificar los pacientes.
No, pero digo yo, así siempre están de mal humor.
Ay, que van a decir, duerme, está ya. Ah, pero es que vos ya que haces algo a la
¿Quién? ¿Quién entra? ¿Cómo es que tomaron la hora? Yo tengo que volver a hacer.
Because it doesn't move. Not all the enemies can come because of the session. Better to take it at the end of the session. Muchachos, cuando terminemos la sesión de la mañana, vamos a tomar un poquito con el grupo, para que no se vayan.
Okay. Everybody.
El que firmó sin
Everybody got their coffee here, good to go? All right, so yesterday we talked a bit about the fact that we can't simulate all of the details directly, and that we have to have some, what we call subgrid models to approximate what we think happens on the very small scales. Right? And we talked also about how this is also done, for instance, for weather forecast simulation or for other things. But also we talked about the fact that these models have maybe some free parameters, and one of the topic of research we also work on is how do we explore, so there can be a lot of parameters, how do we choose efficiently, or how can we explore all of the possible models that we can construct in an efficient way? And what does that tell us about the models and consequences? So just to get us started on this, here is another example, a comparison of different models. So this is from the CAMELS project, and we're going to see a bit more about this in a bit. So this is a project led by the group at the Flatiron Institute in New York. And what they've been doing, they've been asking people that have run different models to run the same chunk of universe with their favorite models. Don't change anything, just run the simulation and tell us what you get. So I showed you yesterday already some example of one single galaxy where nobody agrees. So here's not just one galaxy, it's a bigger region of the universe. And so you have 5 different models. So this is then it's visualized exactly the same way. So cold gas is blue, hot gas is red. The intensity of the color tells you what dense stuff is. Then you have 5 different models that can evolve. You can see the evolution of. So the start is not the same. We can see this model here is already having a lot of hot gas at redshift 6, right? A lot going on. This one clearly has jets that we see in some Asian, some radio galaxies. This one starts later. This one starts very late, so having some hot gas. The one in the middle of the top is really frying up the whole universe. It's like cooking, very high pressure cooking. Right? You're getting a lot of the whole universe is very, very hot. Right? And so we are not even looking at the details of galaxy. We're just asking what is the temperature and the density in the largeness. They're all very different. For sure, at least 4 of them are wrong, and probably 5 of them of the 5 are wrong. Right? So that's also showing there's still a lot of uncertainty of what is going on. In even not even just in the detail of what goes on in the galaxies, even the effect that has on the larger scale structure is very unknown and also very poorly constrained. So based on that, you could say, well, okay, if you want to do precision measurements, cosmology or anything, we should forget about it. We don't know, right? Which one of these is right? Probably all wrong. Which one do we use if we want to compare my data to one of these models? Maybe if we agree with this one but not with this one, what does that tell me? What does that tell me about the theory? Too complicated. So we could say, okay, look, after I've looked at that, I give up. I go on holiday for a few years, and maybe people have solved it in a few years from now, and then I can resume working on cosmology. Or we can try to take a slightly different approach and see whether we can find a better solution. Okay, so I argued yesterday that some of our software models must have 3 parameters because they are sort of parameterization of our ignorance of what is going on the very small scale. And so the question is, how do we find a good value for these parameters? And also, can we then explore a bit what these parameters do, and can we put error bars on our theory as a consequence? So that's what we did so that's a big project. We had a couple of papers this summer out from this Flamingo project, which I think is a supermarket chain right here in Colombia. So it's not that. We don't have a partnership with the supermarkets. I'm not trying to sell you anything. But it's a suite of simulations that are doing very large region of the universe with gas and dark matter and all of the physics we think is necessary. And so one thing we decided to do is to say, I have these 3 parameters in my model that I don't know, that describe some of the details of physics. I want to make sure that I can reproduce some data. Right? I'm going to change the value of my parameters until I get something that I like to look like what I want. So we chose to look like the stellar mass functions, the number of galaxies of a given mass as a function of their mass. And also we asked to have the correct amount of gas within clusters. So 2 data sets. The reason for why we chose those 2, but it's 2 data sets we want to reproduce. Then you can start asking questions like, is the data even good enough? So if you take 3 different set of observations from 3 different groups, asking what is the number of galaxies of a given mass, they don't necessarily all agree. Right? They have different colored lines here. Some of them, it's almost like half an order of magnitude in the discrepancy. So it's not even clear entirely in the data how many galaxies of a given mass there are, but you can still try to live with that. And then what we do is that we run a lot of simulations, run a lot of small simulations where we vary all of these parameters. And so here are 2 examples. I don't even remember what these parameters are. It doesn't even matter. But if I change this parameter here, I can get my model to go through this data point or not. And it doesn't make much of an effect on here. If I change this other parameter here, it changes this, but it doesn't change this one by much. And I have all kinds of very long range of parameters that I can tweak. And some of them will have a big effect on this, some on both, some on none of them. Right? And so I can run many models. And then you can say, okay, now what I want to do, I can try to interpolate it between and try to find what is the best value of this parameter and this parameter, or the combination of all parameters that makes me the closest to the data points I like. And so we do this via machine learning techniques. So we train a neural network to, if I give the neural network the value of my parameters, it's going to make a prediction for what the simulation will look like, and then ask the neural network, give me the best value of parameters to fit the data. And so we can then do some sort of Monte Carlo fitting. We can find some good parameters. We can train this neural network very well. Actually, we were surprised that it worked as well as it did. And then we can find models that go through the data. Right? For instance, here, this red line or this blue line, they go through the data point that I want. They also go to the data point I want them here. This other model also here, right? So we can actually use this strategy to fix our uncertainties. We have these 3 parameters which we don't know what the value are. They are sort of parameterization of our uncertainty, but we have a way of finding good values to give us models that we like. Then we run some very big simulation with the same code that you guys have been using this week. The difference is that they were really big. So I think yesterday, a small simulation that you did had 94 cubed particle. So that's just a bit less than 1 million. The big simulation we did had 5,000 cubed particles. So that's 125 billion. So that's basically 125,000 times bigger than what we ran yesterday as an exercise. And then we also added some neutrinos because that's interesting for cosmology. And so here's just for fun, one of these big simulations flying through. I'm not sure I like that color scheme. We tried something a bit different. Also, it's, sorry, you're gonna get sick. But it shows the usual thing. You have, again, filaments and halos and everything. So somehow we didn't get something completely wrong. I should really make a better video. Okay, and then I mentioned we did neutrinos, and that's quite fun, that's quite unique. So that's just an aside, I'll come back to the parameters before, but we know from particle physics that neutrinos exist. We know from looking at trying to find the best fitting lambda CDM model to the cosmic microwave background, that the neutrinos need to have a non-zero mass, otherwise you don't get a good fit. Well, it's actually not excluded to be zero, but it looks like a non-zero mass is not ruled out. And the neutrinos, they are not like, you can think of it as being sort of dark matter because they don't interact necessarily with the rest. But they're not core dark matter. It's a small component. And because they are very light, they travel at almost at the speed of light. They don't form halos and so on, but they still interact by gravity a bit, and they will still have some sort of non-uniform distribution. So on the right, you have the normal the core dark matter, which again forms the filaments, the halos, and everything that we have seen before. And the same region here would be the neutrino density. So the neutrinos are not completely uniform in the sky, and that can be quite interesting as well, because in the coming years, I mentioned, I think on Monday, that for instance, the Euclid satellite or the LSST telescope are going to be measuring with high precision position of a lot of galaxies. So they're going to be measuring this, but this is influenced in part by that. So you can try to put constraints on massive neutrinos by the simulation as well. Okay, coming back to this free parameters business, the other thing we can do, and that's why this is powerful. Remember, I showed you these 5 different simulations where we don't know which one is correct, but they're all 5 realizations where people say, this is my best guess. And we said we don't want to do this, so of course we got a best guess, we run the best guess simulation, but you can also say, since we have this machine learning approach, and we can ask the neural network, give me the set of parameters that make all of the data 1 error bar away from truth, or 2 error bars away from truth. Right? So I can make a universe, I can ask the machine, give me a set of parameters that will make me a universe where all of the galaxy masses are twice as big, or half as big. Or I can make more gas in clusters or less gas in clusters. Okay? So I can take here, for instance, a model. If I take all of the blue lines here, I have models where the stellar mass in galaxies hasn't changed, but I can vary the amount of gas in clusters by quite a lot. So now what I can do here is that I don't just have a theory prediction, I have a theory prediction with an error bar. So then if people do start to make measurements of something, we can start comparing our data point and trying to see whether it fits within our range or not. Right? So that's sort of an alternative approach to just saying this is our best model, and we're going to just take everybody's best model. We have our best model, but we also have a range of variations around that we can use as an error bar on the theory prediction. And then we also play a bit with, I mentioned yesterday, the AGN jets. Right? So we have different models of how AGN work. So you can imagine that instead of just heating the gas via X-ray, maybe we should model these jets that go through the system. We saw one, I think, I showed you these 5 videos. There was one at the top here that had this jet model. Right? It was very different from the others. So we tried to do also something like that. So we can improve our error bars by not having just one model, but multiple models. One of them including sort of this orientating jets. And so why do we care, right? We can say, well, okay, why do we care about precision, these kind of things? So we've seen many times, sort of a halo mass function. So the number of halos per unit volume as a function of their mass. And we said already that if I change my cosmology, so if I change omega matter, if I change the amplitude of the power spectrum, if I change omega lambda, that curve will change. Okay, so if I go in observations and I have a way of measuring the halo mass functions, say via lensing or via X-ray measurements, and I can do that measurement, I can then compare all of my theory, or sorry, all of my data to my theory prediction, and can then say, okay, my simulation that goes through the data had omega matter equals 0.3. So that's a cosmology measurement of via the halo mass function. One thing which is interesting, and is why we do these variations, is that if I change this parameter that, for instance, changes, right? What I've done here is I've changed the amount of gas in clusters, which is not extremely well constrained by data. What I see here is that my halo mass function changes. So what I've brought in here is the halo mass function in a simulation divided by some reference one. And if I change different color lines here, they change the answer. Okay? So that means that if I now do the experiment I just mentioned, I go in the universe, I measure the halo mass function via some technique, and then you come and tell me this is the number. If I did not take into account this level of uncertainty in the fact that this theory itself has a bigger bar, then maybe we will infer from cosmology estimates. Because if I don't know about this, maybe I'll say, oh, okay, that doesn't have the correct shape, so you have detected that omega matter has to be 0.4, not 0.3 instead. So you made a mistake in your cosmology interpretation because you did not include the fact that gas physics and galaxy formation matters, and that there is some level of error bar in the data. So this is very important. Right? We are now, in the next 10 years or so, all of these measurements coming from Euclid, LSST, the Roman satellite, and so on, they will give us such good data that we have to start worrying about these details, and we can't just live with 5 independent models that are completely different stories. We need to understand the theory better if we want to get a good prediction, a good data inference. Okay, so it's just another movie because why not? Of what the big simulation. This is now the formation of one single cluster. This is let me stop it. So this is so again you have redshift here. Time maybe you can wait this redshift 3.5 now. This is showing you a scale. So this is a bar that is 2 megaparsec. The number will change. You will see how it changes with time. We are seeing the gas in the background here, and there is a zoom in showing you what this cluster here looks like in the dark matter. So you'll see the same thing where the dark matter is way more clumpy. But that's the formation of a really, really big cluster in one of these simulations. You can see this entire region here sort of collapsing and forming a really big, big thing at the end. That's a tiny, tiny region of the whole simulation. And this bar is about the size of the simulation you guys did yesterday. And then this entire box is less than 0.1% of the full simulation. So it's a tiny region, it's an interesting region because it has a big, really, really big cluster forming. At the center of it, there will be a big galaxy. You can see these bubbles expanding. We saw this in multiple movies. The gas, the hot, the AGN activity is blowing out bubbles out of this. So it's just to show you that. So just giving you a flavor of what we did in this Flamingo project, just to give you a flavor of where these big simulations are going. It's really to say we need to run many models so we can characterize our uncertainty and understand what is the level of plausible universes. So we don't change the cosmology, we change all of the rest of the astrophysics and see what is the plausible range of outcomes we can get at fixed cosmology. And so then we can place very nice error bars on the models. Just to give you, so I showed you these 5 parallel movies before. I said this is a Camels project. So the Camels guys, they are doing something similar. So for each of these 5 models, what they do is that they vary the parameters as well. So they take each of these models and they vary everything. They change the cosmology, they change some of the parameters that have something to do with how the stars are formed, how the stars explode, how the black holes are created, and so on. And they vary everything at the same time. They make thousands of simulations, like literally thousands of simulations. And they vary everything, and they see how everything changes. So here are just some examples. I don't know if anyone tried yesterday to plot, I think you tried to plot the star formation history. So, yeah. So in the small simulation, so remember star formation history is what we mean is the number of stars, so the stellar mass formed per year per unit volume of the universe as a function of redshift. Okay? So what they're showing us here is that they have all of these models where they change a lot of different things. So if they change omega matter, so that's just changing cosmology with everything else fixed, these curves change. Right? And one way you can think about it is that if you have more matter in the universe, you're going to form more stars. It's pretty simple, but it's not obvious exactly how this relationship should be. Sigma 8 is the level of fluctuation if you make the universe more clumpy or more smooth. Again, same story. If you make it more clumpy, you're probably going to form more stars and so on. But then you can also see similar variations. If I change one of these parameters, I don't know what that parameter is, something related to supernova, that's all I know. It also has an effect of sort of changing the normalization of the stuff. Same, this one has a different effect. This is changing something to do with black holes. And then they have many more panels where they vary all kinds of other things. And so, this is an even more brute force approach, where you vary everything, and then you say, once I have seen everything, then I'm going to try to train algorithm to tell me which is the correct one, and which one looks like the real universe. Because now what I could do is that if I can measure all of this, and they do this not just for that outcome, but they also measure the stellar masses, or the black hole masses, the gas fraction, whatever, all kinds of things. So if you have all of these measurements from all of these models, you also have the measurement of the real universe. then you can say, what I'm going to do now is I'm going to train a neural network, like using machine learning, on all of these simulations, and then I'm going to ask the neural network to look at the real universe and will tell me what are the values of the parameters. So that sounds very cool, but it's also limited by the amount of simulations. You need a lot of simulations to do this, but you also need a lot of different models, because maybe there's something intrinsic in one of these models that is always giving you the same answer. So that's why they're collecting models from all kinds of people. That's why they have these five different models. For each of them, they run thousands of variations, and then they do this massive training on everything to see whether they can infer something. So that's the goal of the project. I think it's pretty cool in terms of the technology that's involved. And so, for instance, you can start doing these kind of things where instead of even looking at, so this would be, say, assuming I can measure these properties, which is not always, this is not too bad, but some of the properties might be difficult to measure. But if you're going to train a machine learning algorithm, you could say, I don't even need to look at that. What I could do is I can just make images of my entire simulation, like you guys have done. Right? Maybe not of the dark matter, because we can't see the dark matter. If I make images of the gas distribution or the stellar distribution, for all of my simulations, then I make an image of the real sky, and I can ask the neural network, which one is it? We know neurons are very good at distinguishing cats from dogs and whatever. So it's the same idea. If I have enough data, maybe I can ask the machine which one of these thousands of models is the one that looks like the most real universe. And then what you can do is say, okay, you tell me it's this one. Well, this one had omega matter is 0.3, sigma 8 was 0.8, supernova was 5, and whatever. And then maybe you can infer something about, you can learn something about it. You need a lot of resources, and it's unclear at this stage whether it's going to work, but I think it's a fun and interesting exercise of playing with the large amount of data. So you would do something like this, right? You just make maps of something, and then you try to trace something. So by eye, it's not even clear whether you see something, but maybe the machines can infer, maybe the algorithm can infer something that we as humans haven't seen. Would be interesting to know what it is that the machine has identified as an important feature, because we understand the physics as well. But even then, otherwise, we can just ask, which one of these is the real. Any questions? Okay, so I'm just going to finish with a few things about public data, and I think that's also quite nice. In fact, it's very nice. Is a lot of these, these big simulations, they are very demanding. They require a lot of, so these from this camel, they run thousands and thousands of simulations. So they're not very big simulations. You don't need a big cluster for each of them. But if you want to do 10,000 simulations, then you need a big cluster. This flamingo simulation I mentioned before, this one used, what did we run? 30,000 CPUs for 40 days. So that's a relatively big cluster. Some of the other simulations, it's true for many of these big projects. Now the good thing is it has is that people have realized that it's actually valuable for us, but also for the whole community to actually make a lot of this data publicly available, because a lot of people want to use the simulation theory to compare to observations, or to understand something in the data, or just do pure theory projects, and that is very cool. I really like the fact that we put effort into making this happen. And so I mentioned many big collaborations make data available. So the camels that we just mentioned is thousands of simulations. You can download everything if you wanted to. This is the eagle simulation so we played with the eagle model, but the original ones were run with a different code, but still it's entirely available as well. And the illustrious CNG is one of the other big collaborations. They also make all the data available. Now, what does it even mean to make the data available? Because I could give you the snapshots. So this big Flamingo project, the snapshots themselves are 500 terabytes. So 500,000 gigabytes per snapshot. So I can tell you it's available, but that's not very useful, because pretty much if you don't have access to the same computer, there's no chance of making use of this information. So some of these are, okay, these are smaller, but so these you can download on a from your laptop for one simulation, but one simulation is not interesting. The goal of this is to have thousands of them. So you have the same problem. The data volume is immense, right? So what we ended up doing, so this is from the Illustrious webpage, but same is other places, is that there are many, many tools that people make available. So in our case, if I look at Eagles and what I know more about, but Illustrious does the same thing. You can download the full snapshot if you wanted to. I don't recommend doing it because I mean it's too much. But why not? If there's something where your analysis requires to read every single particle and look at every particle, it's there if you wanted to. But very often instead is that we provide already pre-computed information that is useful for most of the projects. So what we have is, for instance, Galaxy and sub-Halo catalogs. So what we have run some algorithms on the simulation to find all of the galaxies. And for each galaxy, we calculate properties. The mass, the velocity, the color, the metallicity, and so on. And that's interesting for people that just want to compare their observation of galaxy mass versus metallicity versus compared to theory. You can just download these catalogs. So it's very often done by SQL type databases. I don't know if you're familiar with this, but it's sort of, astronomers are usually familiar with it because a lot of the observational data is also stored in sort of SQL format. So people are used to querying this, a bit old school, but it works quite well. In this case, these guys are also very nice. They provide you with the Jupyter notebooks. So you can say, give me a notebook, you connect to it, and then it opens the Jupyter notebook on their server, and then you can analyze the data directly on their machine. So you don't have to download if you wanted to look at all of the particles, you didn't have to download everything. You just run a Jupyter notebook on their machine directly. And then there are also things like sometimes just images. In our case, what we have done for Flamingo, we also have done things like what can be quite useful is not to have just catalogs of galaxies, but to make maps of the whole sky. Because compared to observation, you don't want just to know the position, you also want to make sure that how they are correlated on the sky and so on. So we have pre-produced maps, which we use ourselves for our own science analysis, but since we have made them, we're also making the maps available. So this is a lot lower amount of data. So I think there's a lot of cool things that can be done. I really like the fact that people make more of the data available. I like putting the effort into this. They also provide examples. And a lot of these examples are actually better than what I've shown you this week before for the tutorials. These are really cool examples telling you how to run and analyze a lot of things. I think they have examples working in Python, in MATLAB, in Julia, whatever other language you like, to analyze some of the simulation use of the data. So, of course, running your own simulation is fun, but if you don't have, first you don't have to do it. If you just want to analyze something, you can already use existing data, and that's very nice for two reasons. One is because it's alive, but also because already hundreds of projects have used this data. So you're not just using your own. You know that you can compare your results to a lot of other people, and it's put in a broader context of a set of simulations. So yeah, so some of you take pictures. You don't get the slides anyway, but these are interesting links if you want to look at some of these and then make your own comparison to observation or just anything you like. I think it's quite fun. And as I said, data can be accessed in raw form, or Jupyter notebooks, or SQL databases. And there are many, many applications based on this. If you look at the papers coming out every week on the archive, you see at least 2 or 3 every week from people that have not run a simulation but have used existing simulations via this sort of interface to compare, to understand, to analyze or something. So, if you're interested, please go ahead. Or make nice movies. Any questions on that last part? No? Good. So tutorial this afternoon. I forgot whether it was you or you who sent me this one. Because I've seen something like that on both of these screens. One of you emailed me this. So this is from yesterday's tutorial where you're making which you sent it to me. Can you tell us what it is?
It's just the coordinates of particles of dark matter in purple, and in yellow, but in orange we have the stars, the position of the stars. Not density is only position, but density is inferred by the amount of work.
Yeah. Right. So it's just taken from a snapshot of yesterday's simulation from yesterday afternoon. So tutorial this afternoon. I'm not going to be introducing any new things. What I propose we do is that we continue with a similar set of ideas, so we can play a bit more with the simulations. We have these notebooks on Monday and Tuesday. They have session 1 and session 2. There's a session 3 in there, which is also looking at simulation that we've done yesterday, slightly different simulation. They suggest different quantities to look at. So I would suggest, because you guys spent quite a bit of time running the simulation yesterday. Once we have a simulation, it's interesting to look at different quantities. I hope you saw the movie at the start today, where you can color things by different quantities, so you can really get a feeling for yourself of what it is, how is everything distributed. So you can try plotting or measuring all the quantities. There are, again, in the tutorial, there will be a few suggestions about what to do, what you could try, or maybe you can try running some of the other examples in the code. I think one of the cool ones we can do is just a single galaxy list. So it's just one single, there's completely fake universe with just one galaxy, but because it's only one galaxy, you can look at it in more detail than if you have thousands of them. And so I think this is all I have for this morning, and so this is the program for this afternoon. And that's it for me. Can you have a oh, yes, sir?
I don't know, I don't remember if you said it, but how long did it take to run?
So the big simulation took 45 days. So you have breaks in between them. Very rare that you're allowed to use a computer for that long. So we run it for chunks of 15 days. Then you have to stop, let other people do their stuff, and then we can start again for another 15 days, and then we can stop. And so in total, it was a bit more than 45 days.
It was 5,000 to the power of 3 particles.
So it's 5,000 to the power of 3 dark matter particles, 5,000 to the power of 3 gas particles, and then 3,000 to the power of 3 neutrinos. So that's a bit less than 300 billion. So 3 times 10 to the 11 particles combined, if you sum everything. Yeah. Please.
How many people work creating these models?
That's a good question. So it's a complicated question as well. So this Flamingo model, we were, I have a list of names of the people involved, so I don't make any mistakes. So these are the people that have actively been working on it. So 12. Not everybody is putting the same amount. So some people spend all of the time just on that project, and some people are more senior management, and some people at different levels. So it's not the only project I work on. So I'm listed here, but I maybe spend 1 day a week on that. And my student Roy, he spent a lot. He spent 2 years full time on working on this. It depends on work. Now, I should say this is actually not a big number of people for this kind of project. The main reason here is that the model is actually quite simple and is very similar to what we have done. So you yesterday ran this Eagle model, which is a lot more complicated because it has more details in the galaxy properties. Here, this is a lot lower resolution. So what we did is that we took that Eagle model for which we have a lot of experience. So we know that model very well. We know how it behaves. So it didn't take too long to design a variant of that model that is simpler and that can work well. We are working on a different project, which is at higher resolution with a lot more details in the galaxy, and we've been working for 7 years on that other model, of designing the model and getting all of the physics right. Usually running the simulation itself is not the most complicated part of the whole process until the computer crashes or whatever, but usually it's more about designing all of the physics process and make sure you're happy with everything that's going to happen. So for the other project, it's more like 15, 20 people contribution at different levels. So it can be quite a bit of work. And then for the analysis, well, it's sort of the same group of people who are doing our own science case we're interested in, but we also have quite a lot of people since the papers came out saying, oh, yeah, for all this data, I have this cool project idea, can I do it? So we have a lot of things going on. So it's quite fun to see what kinds of ideas that people have that want to do with the simulations. Same with the databases. People come and say, and they have ideas we never thought about doing. So it's also quite- Thanks. Did pick up.
Yeah, well, we're gonna go to the side of the library, take a picture with professor and so let's go.
That is from one of these legal simulations. So it's again a regional university. But what I've done is that I have 5 different bands, and each of them I show something different. So here's the this region here is showing the gas density. Then it's the gas temperature. Then we have the dark matter density, the shocks where the gas is being heated, and then the metallicity. It's just one snapshot, but I'm using just different.
The shows are also the shot.
I don't know if they are in the simulation we ran. Possibly. I think they are. We can check later. It's not called shocks, like